Imagine you're building a system where a user wants to connect an external app like a calendar tool to their profile inside your microservices. To make this work, the calendar app needs to read the user's data. But you hit a massive problem. How do you let the app see the user's data without making the user give away their password? If a user types their password into a third-party app, they suddenly lose all control. Well, they can't just revoke access for that one tool. And if that app gets hacked, the user's entire account is completely compromised. In the previous parts of the series, we talked about high-level architecture and how JSON Web Tokens work. But we didn't cover the most important part, how a token safely gets to the app in the first place. And this is exactly why we use OAuth version 2 and OpenID Connect. They are the standards that let the apps act on behalf of a user completely secure without ever exposing sensitive passwords. Now let's look at why the old authentication methods totally break when you bring external apps into the picture. Well, the biggest problem OAuth version 2 solves is something called access delegation. It's a fancy term for a simple question. How do you let a third-party app access your private files or profile data without giving the app your actual password? In a secure system, you want to give an app permission to act on your behalf, but you want to keep your master password completely secret. In the early days of the web, companies handled this through a method called credential sharing. It was a massive security nightmare. If a new app wanted to import your contacts from your email, it would simply pop up a box and ask you to type in your email username and password. Well, think about what happens when you do that. First, it creates a problem of overprivilege. Once the app has your password, it has total control over your entire account. It can read your private messages, delete your data, or even change your password and lock you out. Second, it forces that third-party app to store your password in its own database. If the company gets hacked, your master password is stolen too. And finally, there was no way to revoke access for just one app. If you wanted to stop that specific tool from reading your contacts, your only option was to go change your master email password. But doing that instantly blocked every other app you actually liked using. OAuth version 2 completely replaces this dangerous model with a system of temporary tokens. Instead of sharing a password, the whole process relies on redirection and explicit consent. Imagine you click Connect the App button. Instead of typing your password into the app, the system redirects your browser to that trusted authorization server. You log in directly on that secure server. Because this happens entirely on authorization server's own website, the third-party app never sees a single character of your password. Once you log in and click Approve, the server hands the token back to the app. The token is built with a limited set of permissions, which we call scopes. For example, the token might allow the app to read your calendar, but completely block it from sending email on your behalf. Well, this changes things, because even if that app gets breached and the token is stolen, the damage is heavily contained. The attacker only gets access to your calendar for a short time. They don't get your account, and they definitely don't get your password. Now that we understand the core problem and how tokens solve it, we need to look at the specific players involved in making this handshake happen. Engineers often talk about OAuth version 2 as a protocol, but it's actually a highly flexible framework. Think of it as a set of standard security building blocks. Instead of forcing you into one rigid workflow, OAuth version 2 lets you swap out pieces depending on your needs. For example, it doesn't force you to use a specific type of token. You can use simple random strings that require a database lookup, or you can use self-contained JWTs that your microservices can verify instantly in memory without calling home. But to map out the architecture of it, you first need to understand the 4 specific actors that make up the framework. First one is the resource owner. This is almost always the human user. They own the data like a profile or order history, and they have the ultimate power to grant access to it. The next one is the client. This is the application making requests on behalf of the user. It could be a website, a mobile app, or a background process. Next, we have the resource server. This is where the user's private data actually lives. In your architecture, this role is played by your individual backend microservices or your API gateway. And finally, we got the authorization server. This is the central engine, the STS or Security Token Service Hub. It handles the login screens, verifies who the user is, and issues the security tokens. By separating these 4 roles, your backend stays clean. Your microservices don't have to know how to log a user in. They just act as a resource server, checking tokens issued by the authorization server. Now these actors need a specific sequence of steps to talk to each other. In OAuth, we call these workflows grant types. Let's look at how they work in practice. A grant type is simply the specific sequence of steps an application follows to get a token from the authorization server. Because a mobile app running on a user's phone has completely different security risks than a backend system running on a private server, the OAuth version 2 provides a couple of standard flows. Each one balances security with the technical limitations of where the application is running. There are 5 primary flows that you will encounter. First one is the authorization code grant. It is the most secure and common flow used for modern web and mobile applications. The second one is client credentials grant. This is used strictly for machine-to-machine communication. There is no human users involved here, and it's just one backend service talking directly to another backend service. The third one is refresh token grant. A specialized flow used by applications to get a brand new access token automatically once the current one expires without forcing the user to log in again. Next one is resource owner password credentials grant, a legacy outdated flow where the user types their password directly into the app. And finally, we got implicit grant, another legacy flow where the token is returned directly in the browser URL. Now, I should mention this right now. You should completely avoid these last two legacy flows in modern systems. They bypass the main security benefits of OAuth and expose your tokens and passwords to major risks. Now, let's look at first and most important workflow, the authorization code grant, and see why it's the safest way to move an identity through the internet. The authorization code grant is the absolute standard for web apps, mobile apps, and desktop software. The main reason this workflow is so secure is simple. It ensures that applications never see the user's password. The user logs in directly on the authorization service page, keeping the master credentials completely private. The secret to this flow is a temporary placeholder called an authorization code. The code is not the actual access token. It is just a short-lived string that the application trades for a token behind the scenes. By using this placeholder, the final highly sensitive access token is delivered through a direct connection between servers rather than being passed through the user's browser, where a malicious browser extension or a network proxy could steal it. The handshake follows a precise sequence. First, the app redirects the user's browser to the authorization server. The request includes a few critical parameters: client ID to identify which app is asking for access, the response type set strictly to code, and the request scope or permissions, and the redirect URI which tells the server exactly where to send the user after a successful login. Once the user logs in and clicks approve, the authorization server redirects the browser back to the application's callback URL, passing the temporary authorization code right inside the URL bar. Now the application takes that code and makes a direct secure call to the authorization server's token endpoint. This is a private server-to-server request that the user never sees. In this step, the application provides the code along with its own private password called the client secret. If the keys match, the authorization server hands over the final access token. This design gives you some massive security guarantees. The authorization code is built for one-time use only. If the server catches an attacker trying to use the code a second time, it instantly kills the code and revokes all tokens tied to it. It also expires incredibly fast, usually in under 60 seconds. Because the real token exchange happens over a direct backend connection, your access tokens are never leaked in users' browser history or address bar. But this flow only works when a real human being is sitting at a screen to click login. So what happens when your backend services need to talk to each other automatically in the background without any humans involved at all? For those automated backend tasks, we switch to a completely different workflow called client credentials grant. When you build a distributed system, your background services frequently need to talk to each other without any human interaction. For example, a backup script needs to fetch data, or an order service needs to push logs to a central login service. For these exact scenarios, we use the client credentials grant. Unlike the previous flow, this interaction happens between only two parties: the applications making the call and the authorization server. Because there's no human users involved to type in the password, this is often called two-legged OAuth. But in this model, the application itself is the owner of the request, but it's not acting on behalf of a user. It's requesting access using its own system identity to talk to general system APIs. The flow is very simple. The application makes a direct secure call to the authorization service token endpoint. It authenticates using its client ID and a client secret, and in this request, it sets a grant type parameter to client credentials. The server checks the keys, verifies the application is legitimate, and immediately hands back an access token. Then the application drops the token into header of its next request calls to target microservices. There is one unique rule you need to know about this flow: it never returns a refresh token. In human-facing apps, we use refresh tokens so the user doesn't have to constantly retype their password to log in. But background services always have direct access to their own credentials stored in an environment variable or a vault. If a machine's access token expires, it doesn't need a refresh token. It simply refreshes the original request and fetches a new token automatically. Because this entire flow relies heavily on the client secret, your environment security becomes very important. These secrets act as master keys for your services. They must never be hard-coded into your Git repository, and they should be stored securely inside a secret manager or a vault. Also, the authorization server should enforce the least privilege principle, only giving the token the minimum permissions it needs to do its job. This handles background automations perfectly, but before we move on to verifying user identity, we need to address the dark side of the OAuth framework, the legacy workflows that you should completely remove from your architecture. To truly understand modern API security, you have to look at these obsolete workflows. There are two legacy grant types that were incredibly popular in the past, but are now considered major security failures: the resource owner password grant and the implicit grant. Understanding why these grants broke will help you avoid massive vulnerabilities in your own architecture. The resource owner password grant was originally created as a temporary breach for legacy apps. In this workflow, the user types their primary username and password directly into the client application. Then the app takes those credentials and sends them over to authorization server using grant type equals password to get a token. This flow is completely obsolete because it violates the primary rule of OAuth, which is never share passwords with the third-party apps. If you use this flow, you're trusting a random client application to handle a user's master password. If that application has a login bug or gets hacked, your user's master password are instantly leaked into the dark web. The second obsolete workflow is the implicit grant. This was designed years ago for front-end browser apps that couldn't safely store a secret key. In this flow, there is no background server-to-server communication. The app redirects the user to login screen with the response type equals to token. Once the user logs in, the authorization server generates the final access token and drops it directly into the browser URL bar as a fragment. A piece of JavaScript then reads that token straight out of the address bar. This is a massive security nightmare for three reasons. First, because the token sits right in the URL, it gets saved directly into the browser's history. Anyone who walks up to that machine can open up the history tab and steal an active session token. Second, if that web page loads any external images or analytics scripts, the token can automatically leak to those outside servers through the HTTP referrer header. And finally, because the token is sitting exposed in the browser global memory, it is a prime target for cross-site scripting attacks. If an attacker injects a single malicious script into your frontend, they can scrape that token instantly. Nowadays, the official industry standard is clear. Never use implicit grants. Now that we cleared out the dangerous legacy options, let's look at the final valid workflow, the refresh token grant. To maintain security across your microservices, your access tokens should be short-lived, often expiring in just a few minutes. This ensures that if a token is intercepted on the network, the window of vulnerability is incredibly small. But forcing a human user to retype their password every 10 minutes destroys the user experience of your app. The refresh token grant solves this. The refresh token acts as a long-lived credential that application can exchange for a brand new access token behind the scenes, completely invisible to the user. The process is a direct background server-to-server request. When your application notices that the current user access token is about to expire, it automatically pauses and makes a secure post request back to the authorization server's token endpoint. The app sets the grant type parameter to refresh token and attaches the refresh token to it saved from the user's initial login. If the app is running on a secure backend server, it also passes its own client ID and client secret to prove its identity. If the refresh token is still valid, the server responds with a fresh access token and the app continues processing user requests. But keep in mind that refresh tokens are not handed out in every workflow. They are included in human-centric flows like the authorization code grant because a human user will eventually close a browser or go offline. They are strictly blocked from the implicit grant because exposing a long-lived master key in a browser URL bar would be an immediate security failure. Because refresh tokens can be used to generate new access tokens for days or even weeks, guarding it is crucial. It must always be encrypted both in transit and at rest. The power of a refresh token is that it gives you a kill switch. This is the primary tool your system uses to force a user logout. If a user clicks logout inside your app, the client sends a request to the dedicated revocation endpoint on the authorization server. The server instantly destroys the refresh token, meaning that the client application can never request another access token for that session. To make this even safer, modern high-security systems use a pattern called token rotation. Every single time your application uses refresh token to get a new access token, the authorization server invalidates the old refresh token and hands back a brand new one along with the access token. This creates a self-healing security loop. If an attacker steals a refresh token from your database and uses it, the real user's next automated refresh attempt will suddenly fail because the token was already used. The authorization server immediately flags this, logs the breach, and drops the entire session to protect the account. Now that we have covered all the ways an application can obtain the token, we need to lift up the hood and look inside the tokens themselves. Let's break down the exact parameters, attributes, and the scopes that make these tokens work. In the OAuth version 2 framework, tokens are the actual keys that unlock your APIs. They allow an application to prove it has permission to perform an action without ever handling or storing the user's master password. Before looking at the tokens themselves, you need to understand the variables that move through the network to coordinate this handshake. These parameters are the instructions that guide the OAuth dance. Client ID is the application's unique public identifier. Think of it like a username for the app itself. Client secret is the application's private password, used strictly in secure server-to-server environments. Response type is used during the first step to tell the server what the app wants back, and it's usually set to code. Grant type is used at the token endpoint to tell the server which flow the app is executing, like authorization code or client credentials. Redirect URI is a critical security guard. The authorization server will only send codes and tokens to the URLs that were pre-registered in the setting, preventing attackers from hijacking the traffic. And the state is a unique random string used to prevent cross-site request forgery or CSRF attacks by linking the initial request to the final response. Once this handshake is complete, the server issues the ultimate credentials, the access token. An access token is a temporary key representing the specific permissions a user has handed over the app. It should never be sent inside the URL when network proxies or application logs can exploit it. Instead, it must be dropped cleanly into the HTTP authorization header as a bearer token. To limit exactly what an access token can do, the framework uses scopes. The scopes are symbol strings that define a clear purpose. For example, a contacts read scope allows an app to view your contact list, while contacts write allows it to create new ones. During the login process, the user sees these scopes explicitly on the consent screen and must click approve to delegate those exact rights. The authorization server can also override the app's request, cutting down the scopes based on company security policies. While the purpose of an access token is always the same, an internal architecture can follow two completely different patterns. First one is reference tokens or opaque tokens. The reference token is just a random meaningless string of characters. It carries no data inside it, and when a microservice receives one, it cannot read it. It must pause and make a network call to the authorization server's introspection endpoint to ask, is this random string valid and what permissions does it carry? The benefit of it is absolute control. If you want quick user out, you simply delete the token from the central database and it stops working instantly everywhere. But the downside is high network cost. Every single microservices call requires a round trip back to the central server, creating a massive bottleneck. The second way is self-contained tokens with JWTs. A self-contained token carries all of its data directly inside its payload. As we covered in our last JWT video, it holds the user ID, expiration timestamps, and scopes in signed JSON structure. But the benefit is extreme scalability. Because your microservices already have the authorization server's public key, they can verify the digital signature instantly in memory. No database lookups, no external network calls, and it's perfect for distributed microservices. But the downside is that it's harder to revoke. Once a JWT is signed and sent out, it's valid until its expiration timer runs out, because services check the signature rather than a central database. As an architect, you balance this trade-off by using both sides. You issue short-lived JWTs as access tokens, lasting only 5 to 15 minutes, and pair them with revocable refresh tokens. If you need to cut off access, you revoke the refresh token at the central server, so the client can never fetch a new JWT once a short-lived one dies. Understanding these token formats helps us to see how permissions travel across our network. But look at this major gap. OAuth version 2 only tells your services what the bearer is allowed to do. It doesn't actually tell them who the user is. To fix this missing identity layer, we have to look at the protocol built directly on top of the OAuth, which is OpenID Connect. A common mistake engineers make is that they try to use OAuth version 2 to log the users in. But OAuth version 2 on its own is purely an authorization framework. It gives an app a key to open the door, but it doesn't actually tell the app who turned the key. To solve this, the tech industry built OpenID Connect or OIDC as an identity layer that sits right on top of the OAuth version 2. While OAuth handles the permissions, OIDC handles authentication, the process of proving who the user is. The biggest upgrade OIDC brings to the table is a brand new token called the ID token. An ID token is always a JSON web token. Its entire job is to carry profile information about the logged in user from the authorization server directly to the client application. Because it's a self-contained JWT, your application can parse it and read the user's data instantly in memory without making a single network call. Every ID token is packed with a specific standardized claim that give your application the user context. ISS or issuer is the URL of the security server that created the token. Sub or subject is a unique, unchangeable ID for the user like the internal user ID. AUD or audience confirms exactly what client application this token was built for. EXP or expiration and IAT or issue that tell the app exactly when the token dies and when it was made. Nonce value is a unique random string passed by the app during login and stamped into the token. The app verifies this string to prevent replay attacks, ensuring an attacker didn't just grab an old token and try to resend it. And we have AZP or authorized party. If a token is allowed to be used by multiple services, the claim specifies that exact client application that originally requested it. OIDC also includes audit trail claims like auth time, which is exactly when the user typed their password, and AMR, which is authentication method reference, which tells your app exactly how they log in, such as whether they use a standard password or a secure multi-factor biometrics check. To activate these identity features, your application just needs to add one specific string to its initial login request, the OpenID scope. When the authorization server sees scope equals OpenID, it instantly knows that this is an OIDC handshake. If you're using the gold standard authorization code flow, the server will hand back the temporary authorization code. When you app traces that code at the token endpoint, the server returns a package containing three things: your standard access token, an optional refresh token, and your brand new ID token. But what if your application needs more detailed user data than what fits inside the standard token payload? OIDC provides a built-in solution called the UserInfo endpoint. This is a secure API hosted right on the authorization server. Your application can call it by passing the standard access token in the HTTP header. The endpoint will look at the specific identity scopes that the user approved during login and hand back a clean JSON object containing the profile data. This data includes profile, which hands back the user's name, preferred username, and profile picture URL, email, which hands back the verified user email address, and phone and address, which hands back the verified phone number or physical location coordinates. Now that we have full identity layer in place, we need to look at the advanced security extensions required to protect these handshakes from modern network attacks. Once you have the basics of OAuth and OpenID Connect down, you need to protect these handshakes from modern network attacks. The browser and the user's device are inherently untrusted environments. To lock them down, we use 3 advanced security upgrades. The first and most important is PKCE, which stands for Proof Key for Code Exchange. Originally, PKCE was built just for mobile apps, but today under the new OAuth 2.1 standards, it's mandatory for almost every application using the authorization code flow. PKCE prevents a specific hack called code interception attack. Imagine a user has a malicious app running quietly in the background of their phone. When the authorization server sends the temporary authorization code back to the browser, the malicious app could swoop in, intercept the code from the device operating system, and try to use it to steal the user's tokens. Basically, it stops this with a clever math puzzle. Before the client application ever redirects the user to log in, it generates a secret random string called a code verifier. Then it takes that string and hashes it to create a code challenge. When the app sends the user to log in, it attaches the code challenge to the request. The authorization server looks at it and saves it. Later, when the legitimate app receives the authorization code and goes to trade it for tokens behind the scene, it passes the original raw code verifier. The authorization server runs the exact same hash functions on the verifier. If the math matches the challenge sent earlier, the server knows for a fact that the application asking for the tokens is the exact same application that starts the login flow. If a hacker intercepted the code, they wouldn't have the secret verifier and the token exchange would fail instantly. Second upgrade is PAR, or pushed authorization request. Traditionally, when an application starts a login flow, it jams all its setup parameters like client ID, the requested scopes, and the redirect URL right into the browser address bar as a query parameter. But this is very risky because these parameters sit out in plain text where they get saved into browser histories, caught by network proxies, or tampered with by a malicious user. PAR totally flips this model. Instead of routing everything through the browser, the client application handles the setup over a secure backend pipe. It pushes all those sensitive login parameters directly to the authorization server through a private server-to-server call before the user even sees the login screen. The authorization server validates the request, saves the parameters for itself, and hands back a temporary random reference ID. The applications then redirect the user's browser using just a harmless reference ID. This keeps your sensitive architecture details and request scope completely hidden from the browser. And finally, we have JAR, which stands for JWTs Secured Authorization Request. This is another powerful way to protect your initial request detail. Instead of passing parameters as plain readable text over the web, the client application wraps all the parameters inside the JSON web token and signs it with its own private cryptographic key. When the authorization server receives the package, it checks the digital signature. This guarantees 2 things. The server knows the request came from your legitimate client application, and it knows that not a single character of those parameters were modified or tampered with while traveling to the user's browser. By layering PKCE, PAR, and JAR onto your architecture, you move far past basic token security. You ensure that your microservices system is fully hardened against modern web interception and tampering attacks. Well, this is it. We have now covered the complete blueprint for how users and applications interact securely in a distributed system. We started with the core problem of access delegation and saw how the OAuth version 2 frameworks uses specific actors and workflows to pass temporary tokens instead of master passwords. We looked at how OpenID Connect fixes the missing identity layer by introducing the ID token and the UserInfo endpoint. And finally, we looked at how advanced upgrades like PKCE, PAR, and JAR completely harden these handshakes against modern web attacks. Well, I know this is a ton of information, but what we broke down today are exactly what you need to build and defend production-grade services. Mastering this flow is the ultimate stepping stone to securing your entire backend. Well, if you found this video helpful, please like the video and subscribe to the channel, drop any question you have in the comments, and see you in the next one.